Okay, so you have to take note that the EMF is proportional. Sorry, the EMF production is proportional to the speed. So speed is N. So N is in RPM. It's not radian in second. So from the in the system, you need to take into account that the total line resistance Rx, R sub X is 3.194 ohm. You have total line inductance 1 millihenry, and the objective of the converter is to transmit 7 kilowatt to the AC source, to mean from the DC to AC. And you have to limit the current ripple, the output current ripple, which is 10% of the average load current. So the load current given is 25 ampere. So in your design, you need to obtain some operating parameters, control parameters, for example, alpha, and the output voltage, the power absorbed by the bridge, power losses, and absorbed by the resistance. So this case, you have two resistance, which is armature resistance and line resistance. And the other two resistance. Okay, so in your design, you need to use the graph given here in order to estimate the voltage harmonic. Okay, so this is the system, the structure of the system. You have the AC source here. This is the AC source, AC system. And here will be the DC, DC side or DC network lah, DC network. So you can notice all these elements which are Rx and the line resistance, line inductance Lx, Lf is the inductor that you need to design. You need to calculate or obtain the appropriate value of inductance in order to limit the current ripple. So the Lf. So this dash line array is the DC generator. And so remember your DC motor. So we can assume this motor as a permanent magnet. It's not the one motor. It's the permanent magnet. So the magnetic field is constant. So in the magnet, you can model the DC as three elements here. RA, armature resistance, armature inductance, and the EMF, where these three elements are connected in series. Okay, so the objective is to transmit the power from DC side to AC side by 7 kilowatt. Right? Before this, we discuss exercise where the DC source is solar cell or solar panel. But this case, the voltage produced from the DC generator. So mean you need to calculate the required speed in order to produce the desired voltage in order to transmit the power by 7 kilowatt to the AC system. Okay, so this is the three-phase, 6-pulse converter. Means it consists of 6 thyristor or SCRs. Okay, the solution. Ini suppose saya dah provide. So please understand. Okay, first, in order to obtain all the control parameters, operating parameters, a set of operating parameters. So firstly, you need to calculate the VO, the required output voltage. So you must take note that the VO definition, which is the different voltage between here, plus to minus. So this is the VO. Clear? This is the VO, where the output terminal of the bridge. So remember to put plus at the bottom, minus at the, plus at the top, minus at the bottom. Okay, then you calculate the PO. So where the PAC, the power absorbed or power to be transferred to the AC is given, which is 7 kilowatt. Clear? 7 kilowatt. So then you can simply calculate the VO by ni lah. 7 kilo divided by output current. So where the output current is given, which is 25 ampere. Betul? So then from here you get output voltage. So the output voltage must be negative because this converter operates as an inverter. And so make sure the output voltage must be negative. So then next step, you apply this equation. Okay. So this is the three-phase rectifier. The output voltage from the three-phase rectifier. So you must multiply by 3 VM, VM line to line. So you rearrange this equation then to calculate the alpha. Okay, then you get the angle is 120 degrees. So make sure in your solution, you put in degrees. Okay, then because after this you need to estimate the voltage harmonic. So you must apply the alpha in degrees. Okay, then next step, calculate the EMF voltage and the required speed. So where the EMF is given as multiplication between EMF constant KE and speed N. So N must be in RPM. So from here, you can draw the simplified circuit first by neglecting the inductor because we try to do the DC analysis. So you ignore the effect of L. So then you get this circuit. So take note, your polarity of EMF must correct. If your EMF is positive, and you put the value is positive, means the plus must be at the bottom. Okay. If EMF given is negative, and for example, assignment kan? Assignment midterm test question number 2 last week. So you must change the polarity of the DC source because the value is negative. This case, EMF you calculate is positive. So then you need to put the positive sign at the bottom. So then from here, you can calculate what? You apply Kirchhoff voltage law, sorry, in order to calculate the EMF. Okay, this one just applying the Kirchhoff voltage law, then you get this equation. So then you rearrange the equation, then you get EMF is 374.85 volt. So where we know that EMF is multiplication between EMF constant and N. So then from here, you can calculate the required speed and the required speed. So then from here, you can obtain the speed in RPM, which is 1,500 RPM. Okay, then you need to calculate the power absorbed and power losses. So here, the power delivered by the DC generator, which is PDC, you multiply between EMF and IO. Okay, betul EMF. So then you get 937 watt, 71 watt. Then you also need to calculate the P losses, the power absorbed by RA and RX, the armature resistance of the DC generator, and the line resistance, RX. So then you calculate, you get 2371.25 watt. Okay, then you can check your answer by subtracting between these two values, PDC and P losses. Then you get 7 kilowatt. So make sure 7 kilowatt, same as given in the question lah. Because you need to transmit the power from DC to AC, or the power absorbed by the bridge must be 7 kilowatt, as given in the question. So this is how you check your answer. Okay, clear? So you need to calculate all the operating parameters, the alpha, the IO, VO, EMF, the required speed, the power absorbed by the bridge, power losses, okay, and so on. Okay, then in order to limit the current ripple, so mean you need to put LF here. So you can see here, LF, the filter inductor. You mean you try to increase the inductance, the inductance. When you increase the inductance, so then you can minimize the current ripple. You can minimize further the current ripple. So this case, this part you need to calculate the required LF. So based on the specification given, so you have to limit the current. So must be about 10% of IO, the average current. Okay. Okay, then here, okay, so you need to write here, you need to put assumption and make sure you write the assumption that you apply to solve the problem. So assume the variation in load current is mainly due to the first AC term. And for the three phase, the first AC term is I6. And three phase for single phase, I2. Okay. So then here you calculate the current limit, which is 2.5 ampere. So we know that the peak to peak current variation is 2 times of peak of the first AC term, I6. Okay. Okay. So then from here you can calculate the peak of the first harmonic component of current, which is 1.25 ampere. Okay, then here you estimate V6 from the graph. So based on the calculated alpha in previous part, so where the alpha is 120 degrees. So from here you can get the normalized harmonic voltage, which is 0.28. So you rearrange this equation to calculate Vn. Okay, don't forget you must know how to calculate Vm line to line, because this is the three phase. So 450 volt is line to line voltage. So you need to multiply by set 2 to calculate the peak value of Vm line to line. So then you get V6 is 164.33 volt. Then from here you can calculate the required load impedance for N equal to 6, Z6. So then you get 131.464 ohm. Okay. Okay, so then you need to write this statement. Note that the total resistance, which is summation of RA and RX. So in this case, you have two resistors. The armature resistance of the DC generator RA and RX, line resistance. So you get 3.794. So where this value is too small compared to the total impedance, 131.464, then you can ignore this term. Okay. So then you rearrange. Finally, you can calculate. You can calculate the total impedance first. Here. So we know that the total impedance, total inductance, total L, total inductance is summation of LX, LF, LA. You ada three inductance, armature inductance, line inductance, and the required filter inductance. You ada additional LF. Okay. Okay, where LX and LA are given, LX and LA are given, then you can calculate the required filter inductance, LF. So then you get 0.0567. Same procedure, kan? Like fuel cell of solar cell. The only difference is for inductor you have additional term here, LX, LA, LF. Clear? And also the total resistance, because you have RA and RX, the armature resistance of DC generator RA and the line resistance. And one thing, the only difference is, another difference is, this case you need to calculate the required speed, because the production of the voltage from the DC side based on the speed, and depends on the speed, because you need to produce the EMF voltage, where the EMF is proportional to the speed. Okay. Okay, clear? That's it. I don't need to discuss detail. I just give this answer. Then you need to try to understand and practice without looking the answer. So please. Okay, for verification. So this is the simulation of the exercise. So here is the inverter, 6-pulse converter. You have here at the DC side, you have RX, LX, LF, and the DC generator. All these component or elements are connected in series. So this is the DC generator in order to produce the voltage across these two terminals, VA plus to VA minus. So the production of the voltage is based on the speed. So the speed is given based on your calculation, which is 1500 RPM. Okay. So this is how we model the DC generator. Very simple. Because this I model simplified model. Because we consider for DC analysis, no need to design for the mechanical part lah. The moment of initial visual friction. Kenapa Padam? Okay. So here speed in RPM, then you need to calculate with this one. I think is KE. So you can refer from the question. KE is given in RPM. Sorry, voltage per RPM. So because your speed in RPM, you multiply voltage per RPM, then you get the voltage here. So this block actually will produce the voltage, which is proportional to this signal. Okay, where this signal is multiplication between speed and EMF constant. So this is the EMF constant at this block. Okay, then, okay, the angle here is 120 degrees. So this is the firing angle unit. Sorry. Which one? So here is the firing angle unit, this block, which is responsible to generate the current pulses here. And to control 6 thyristors, T1 until to T6. Angle 120, frequency is 50 Hertz. Okay, now we can run the simulation. Okay, before that, here is the line-to-line voltage. Sorry, this is the phase. You need to convert into phase first. Because this block, the parameter block required to put the value, the peak amplitude value. So means for one block is the phase voltage. So you need to multiply by, you need to divide by square root of 3 to get the phase voltage. Then you multiply by Z2, square root of 2 to get the peak value. Okay. Okay, run. Okay, so here is the output voltage. So you get what? Based on calculation is minus 280 volt. Is that right? So the current is almost close to the calculation value, which is 25 ampere. Okay. So this is the waveform. And the waveform ni. Okay, this is the waveform of the output voltage. Because this converter operates as an inverter, so then you can notice the output voltage below the time axis. Oh, sorry, where the area, the negative area is produced to get the negative output voltage. Okay, the white color here. Okay, any question? That's it for today. Okay, I think I need to discuss about the assignment. The assignment, because we have do apa? Sorry, macam mana nak minimize ni? How to minimize this window? Gosh. Yeah. Okay. Okay, for assignment, let me open the task. Assignment, where is the assignment? Correction, this one, correction version. Because last time, we reduced the voltage, right? From 120 volt to 75 volt here. So make sure you do the first part, part A, to calculate the on time information TA apa? TA, TB, TZ kan? For one complete cycle of switching period. So in this case, you need to put constant value of input of the modulator. You're gonna put, because in this question, you need to calculate the on time for a particular instant. So mean your controller sample the input signal for one at a particular instant. Then you need to to calculate. Firstly, you need to plot the waveform the switching status waveform. Then you analyze the time difference to verify the result with the calculation the on time. Okay, there's one part A, part B, part C. I think most of your groups done this part. Very simple. Maybe you just take only 1 hour to complete for part C. To run the hardware to adjust the motor speed. Okay, this one no need. For part C, I forgot to plot the switching status. This one no need. You may cancel this part. Is it right? Okay, no need to plot the switching status waveform and measure analyze the on time using the oscilloscope. Okay, this part no need. Okay, you just record and save the waveform for phase voltage, phase current, and frequency spectrum of output voltage for 3 different speeds: low, medium speed, and high speed. That's it. Okay, clear? No need to plot the switching state waveform using the oscilloscope because it's difficult and takes time. Okay. Okay, for the simulation, because after you get the experiment result, then you need to compare with the simulation. Okay, let me show you. Because okay, this is the simulation. Okay, so this is the inverter. So let's say I put the motor. Okay, you can notice this part is different based on our discussion during tutorial session. Because in order to adjust the motor speed, this case we apply the simplest technique, which is V per F control or scala control. Just open loop, open loop scala control. So mean you just only control one parameter, which is the fundamental component. So at the same time, the frequency also varies according to the fundamental component. So please understand how I designed this block. So this is the modulator that you have designed. Clear? Clear? Same with the simulation that we have discussed in tutorial session. So where this input, the input of modulator are VD and VQ. So you have the sign block here to calculate VD and VQ to calculate VD and VQ. So you can, based on this equation, so where VD is peak, VM is U1, sine omega t, 2 pi. So mean U2 is frequency and U3 is time. So time we obtain from the clock, Simulink block and clock. You just search this block to represent the time. Okay, and to design for the time lah. Okay, for VQ, you need to additional term minus pi per 2. So remember D and Q, the different phase must be 90 degrees. Okay. Okay, so U2 is frequency. So this I use the Dmax block. Max block, where you can have multi input but single output. Okay. So where this line carry 3 signal U1, U2, and U3. So where U1 is the fundamental component, V1 V1. And the second here is frequency. And this signal is time from the clock. I try to understand how I design this block. Scala control technique. Okay. So where this gain value is actually is ratio between the frequency and the maximum fundamental component. Okay, where the maximum fundamental component is 43. Because of what? Because we agreed to set the DC voltage is 75 volt and 75 volt. So mean your maximum of the fundamental component should be here. And VDC divided by set 3. So then you get 43.3013. So you cannot set the fundamental component beyond this value. If you set beyond this value, so all the on-time information, the calculation that we have used to model are not valid. Not valid. So make sure you set the fundamental must be lower than the maximum, 43 point something. Clear? Okay. Okay, so the way to adjust the speed actually because we just run for no load case. So your TM is the load torque. We just put 0. So that's why when you go to my lab and so your motor is free running. You do not connect with the load and just free running and no load. So where the speed, you can calculate the speed by using equation what? 120 multiplied by frequency divided by number of pole, I think. Number of pole, is it right? 120 multiplied by frequency divided by number of pole. Okay. So we assume the speed is same as the frequency, the fundamental frequency, because there is no load. Okay. Okay, so means here, sorry ni. Okay ni. So means if you set this one, this value is the maximum 43.3013. Okay. So then you multiply to this block to get the frequency, then you get 50. The maximum is 50. So mean your motor is running at maximum speed at 50 Hertz and the rated frequency. Okay. So if you set this one, let's say you set 10. Okay. Then you get what? The value of frequency here. So the frequency also will be reduced. If you set higher fundamental, so same goes for the frequency. The frequency also will be increased. So actually every value of the variation value of the fundamental, we try to maintain this ratio. So that's why this technique refer to V per F. We maintain the ratio of V per F. Okay, V per F. Boleh faham tak? Tulis ni. So maybe here. Okay, this is your scala control. Scala control. So V per F. We try maintain this ratio as a constant. Constant value. Means if your V increase, your frequency also increase. Is it right? If you try to reduce the frequency also reduce, then your speed will become slower. So this is a very simple technique. No need to use the vector control, FOC, directed control, no need. Okay, we just apply the VF technique. Okay, so to plot the frequency spectrum, okay, let's say here this block, this one may be push button block, I don't think. So we can set for low, medium, and high speed. The low value is 10, medium is 20, and high speed I set the fundamental is 30. So when I increase the fundamental, the frequency also increase. And the frequency also increase. So means the speed of the motor also increase. Clear? Okay, so let's say, let me try to run the simulation first. Macam mana buat? Let me resize the window. Okay, this is the scope. Okay, initially I set the speed at low speed. We try to analyze for 3 different speed, low, medium, and high. So when I set low, so mean the value here will be 10. Maybe I need to magnify this part. Macam mana nak scroll? Sorry. So here ni. Saya magnify this part. Okay, for low speed, initially I set low speed. So this means the fundamental value is 10 volt. The frequency will be 11. Please calculate 10 multiplied by this gain. 10 multiplied by 50 divided by 433.30313. Then you get 11. Okay. So let's say I run. Okay, initially the speed is low because I set the fundamental value is 10. The fundamental voltage is 10. Okay, run. So at the same time, please observe the waveform. Okay. Okay, this one for 10, low speed. So this is the speed waveform. So then I change to medium. Right? Okay, medium. So then you can see the speed will be increased. Okay. So the speed increase, your frequency, the fundamental frequency will be 23 Hz. Because 20, you multiply by this constant, then you get 23 Hz. So then your motor speed will be increased. Okay, then I click high speed. So once I click high speed, so the fundamental frequency also will be increased. So same goes to the motor speed. Okay, this is the simplest control technique, where we control both frequency and the fundamental component. Okay, okay, stop. Okay, then auto scale. Then you can see the profile of the speed. So here when we set the low speed, where the fundamental is 10 volt, then you change to 20 volt here. So then your speed also will be increased. For initially your voltage V1 is 10, frequency will be 11 and 11 Hz something. Then you click medium speed, the fundamental is 20 volt. Then your frequency will be what? Maybe 22 tadi, 22 something. Then once I press high speed, means we change the fundamental component to 30 volt. So when 30 volt, the frequency also, the fundamental frequency here, also increase to 34 point something. Then your motor speed also increase. So that's why we call this technique as a V per F. So we adjust both voltage and frequency. Okay, clear? So please understand how to construct this block. Okay, for your assignment, you no need to model this part. This just for your knowledge lah. No need. But to compare the experiment result, I think I need to open the file first. The file. Assignment. Okay, this. And no need to put the motor. You can represent the motor using R load or RL. Just passive load. Here. This. Okay. So this is your control algorithm SVM. Here is the load. So you just use maybe R load only is okay. Clear? No need to put the motor. Okay, so here, let's say because in lab and in my lab, because I already set up the based on the video and video guideline kan. So you need to analyze for 3 different speed. Low when the fundamental is 10 volt, medium speed when the fundamental is 20 volt kan. And to run high speed, you need to set the fundamental 30 volt. 30 volt. Okay, this case, let's say 30 volt. So means the motor will be run at high speed, 30 volt. 30 volt. Okay, then you get the result, result FFT. So after that, you need to compare the experiment result with the simulation. So I want to show you how to do a proper setting and to get the frequency spectrum of the output voltage. So let's say we try to do for high speed first. Let's say in this case, your fundamental, you need to set 30 volt. 30 volt, 30 volt. Okay. Okay, when you run, 30 volt. So firstly, you need to calculate the frequency here. So what you get? This frequency. Okay, saya try ni, saya tunjuk. Okay, so this is, okay, from here, you can calculate the fundamental frequency, which is what? 30 volt multiplied by 50 divided by 43.3013. Okay, so this is the frequency here. Right? Okay, to run the simulation, ini penting to run the simulation, you need to set appropriate value of stop time. Stop time. So let's say we try to analyze the waveform or run the simulation for 5 cycle. Ni, kita tengok ni 5 cycle ke saya buat? Oh maybe sorry 3 cycle only, 3 cycle. So means from here to calculate the period, so you need to invert kan, 1 divided by F1 for 1 cycle. So then you set your stop time. Stop time, you need to set stop time. So this case, I set 3 times. 3 times T1. So please understand this one. Okay, F1 here, from this line kan. You calculate F1 because you need to apply the value of F1 to be substitute to this equation. You have 2 pi F kan. So mean F is F1. And from the MATLAB function block. Clear? So then you calculate T1 first, which is inversion of F1. Okay, then you run the simulation until 3 times of T1. 3 cycle of waveform. Boleh faham? So you tengok kat sini. 3. Then you divide by 30. Betul lah. 30 multiplied by 50 divide by 43.3013. Boleh nampak? Okay tak? Stop time. You kena set proper value of stop time. Because you need to get the FFT tu. Okay, clear? So then you get this one. Okay, then you try to run the simulation. Okay, run the simulation. Lambat pula. Maybe I need to close. Okay. Okay, 10%. First you need to change the punya model the input model ni. Because when you run the experiment, you apply the V per F technique. But you still remain, the modulator you remain. And based on our kita model and discuss during tutorial session. This part you remain. And this part you remain. The only part you need to change here. Simple, very simple. Because kita nak compare with the experiment. Your experiment, your motor running using this technique, skala control, V per F. Okay, clear? Okay, wait until the simulation is completed. 100%. Nampak lagi. Sikit lagi, sikit lagi. Okay, first, you kena change the input ni. Sebab you nak apply skala control, okay? Yang tu, first thing. So, try to model like this. Then, second, set appropriate value of stop time. So, mean you try to analyze the waveform for 3 cycle of the output voltage. So, that's why you kali 3 tu. And third, ni. Third, because you nak plot the FFT, okay, you double click the power GUI block. So make sure your punya running is completed. You double click this block. Okay, ni apa? So then go to the 2 step and same thing lah, FFT analysis. Okay, ni. Okay. Okay, you need to set ni, the fundamental frequency in this parameter blocks here. Nampak? Boleh ni. Boleh tak? So your fundamental is, because 30 is your fundamental. You set fundamental tadi, voltage is 30 volt. Then you multiply by the ratio ni. 50 divided by 43 something. Then you get the fundamental frequency. So you need to set this appropriate value of the fundamental frequency. If not, you get the wrong answer. Boleh? Clear? Understand? You get what I mean? Okay, clear? Faham? You ada 3 procedure apa ni kan? 3 parameters that you need to set properly. First is the stop time. So make sure you running for 3 complete cycle. Before that, you need to calculate the fundamental frequency first. Then you get the period, right? Then you times 3. And you try to run for 3 cycle of the output. Okay, then the second is what? Set the this box, the fundamental frequency from the power GUI ni, FFT window. So this is the fundamental frequency. Clear? Maksudnya you multiply between the fundamental voltage and the ratio. Then you get the fundamental frequency. Okay, then after you set appropriately, then you can click display button to plot the FFT. Okay, you get this result, then you compare with the experiment result. Is it match or not? Okay, so this is for the case of high speed. For low speed, same thing. You need to change. Okay, let's say medium is 20, right? Okay, let's say I show for 10 volts. Low speed. So means here your fundamental will be smaller, right? So you need to multiply by this one will be 10 kan? Is it right? 10 volt. This ratio maintain because you multiply from this block, the gain block. And the ratio is maintained. V per F is constant. So then you multiply, you get F1. Then you calculate the period. Then you need to set your stop time here. Stop time. Here you need to change to 10. Means you try to run analyze the result for 3 cycle of the output voltage, output current. Okay, clear? So then next step, you need to set appropriate value of the fundamental frequency in this window. Here will be 10, right? 10. That's it. Okay. Understand, eh? Okay. Alright. Okay, for those group that have not come to my lab, so you can come this week. Can just private message me to set the appointment. So I'm free this evening. I'm free. Tomorrow morning, okay. 9 to 12, 9 to 1, okay. But in evening, maybe we have radiate. Thursday evening free. Okay, ada apa nak tanya? Kalau tak ada, kita boleh tamatkan our lecture. Alhamdulillah, habis pun. Okay, after this, I will compile all the material for lecture notes and tutorial. I compile, then I can share to you lah. So please read and do the exercise. Without looking the solution and try practice. You want to score A in this subject. Okay, so please do. Okay. All right. Thank you. Assalamualaikum.